All right, so we're back again. Going to move into our new chapter, chapter 11, randomness and understanding randomness. And this is how we're going to concentrate on how we use random numbers as a tool to ensure we're being fair, how we avoid bias. And this one, we're investigating things that go on in the real world. It's about different models we can use, how do we use the Texas Instrument calculator to generate random numbers, and also how you can use a random number table. So first thing is, random selection is fair because nobody knows the outcome for sure before it happens. Now, if you did know the outcome ahead of time, we could be influencing the results. We could choose different models to use, and we'd be introducing bias into our samples. Now, in order for this to truly be like a random, what we're looking for is that all the different possible outcomes have to be equally likely. And that's the way we'll know it's random selection. All different outcomes are equally likely. Like I said, if I was randomly picking two people out of the class, I would have the same chance that a group of person A and person B as a chance of getting person B and person C. All different outcomes would have to be equally likely. Now, like I'm tossing a coin. If we say I have to toss a coin, the heads, tails, equally likely. So if someone handed you a coin and said it was biased towards usually landing on heads, you'd probably be pretty skeptical of that. So what would you do? Well, to be honest, you'd probably flip the coin a few times. Oh, sorry about that. You'd probably flip the coin a few times and see. But the question is, how many times would be enough? If you can flip it 3 times in a row, would you be persuaded that coin was biased? Maybe not. 3 could happen just by chance. I could get heads 3 times in a row just by chance. What if it was 7 times out of 10? Just 7 times out of 10, not necessarily in a row, just 7 times out of 10 I got heads. I expected it to happen 5 times, but 7's not, completely ridiculous. I'm looking for behavior that's inconsistent with my beliefs about it. I believe the coin should turn up about 50% of the time. So let's say I flip the coin 100 times. Would 54 out of 100 convince you the coin is biased? Maybe not. How about 60? Maybe 60 would, or 95 out of 100? At this point, I'd probably say, yeah, the coin's biased. 95 times out of 100 I get heads. Yes, I believe there's something going off that coin. But what if it's 80 out of 100 or 70? I can decide where we're going to draw that line. And right now, you're kind of making a personal decision. What would it take to convince you the coin is unfair? We're relying on our gut instinct. The question is, where should we draw the line between something that's reasonable, it could happen, and something that's so strange, we think it would basically prove there's something wrong. Something was so rare that to me, it would let me say, yeah, I don't think this coin is a 50-50 coin. I don't think it's a fair coin. Well, we can use the calculator to simulate some random numbers. In fact, if I run this command, randint, and I tell it 0, 1, I can have 0 represent tails and 1 represent heads. And specifically, the way this would look, so I pull my calculator, and I press math, go to PRB, randint, and I tell it I want it to be 0, 1. So I want 0 or 1. That's what I want to do. It's a random integer. If I run this, well, I predict I'm going to get 1. No, that can just kind of happen. What if I got another 1? Or a 0? Or a 1? Or a 0? Okay? Now your audio is not out of sync. Just that I'm just that good. But, let's make it a little bit harder. I get a 50-50 chance of guessing right. I could have guessed right 5 times. I can do a random integer again. And let's just say this time it's going to be between 1 and 546. And I think it's going to be 401. Or maybe it'll be 25. Or maybe it'll be 186. Okay. What we're seeing is the calculator doesn't give us truly random numbers. In fact, I was able to predict it ahead of time what we were going to get. So instead what we have to do is the calculator, it's giving us what's called pseudo-random numbers. So instead we have to seed the calculator. We're going to put something in the calculator as a random seed so that the numbers it'll give us will be different than another calculator. Because if I reset all the calculators, we're going to get the exact same sequence of numbers in the same order. So I pull up my calculator and I'm going to seed it. And what we normally do is the birth date. So for mine, well, it doesn't really matter what my birth date is. So I'll just put in some numbers. And then I press stow. And then I need to store that in the random. So I go math, PRB, rand. I press enter, it shows me that number again. Now my calculator has been seeded. If I run that random number generator again, I could not predict what it's going to get. 1. Nope. Well, 0 again. Hey, I got it. Okay. Another 0. No. Okay, I can no longer predict it because it has been seeded. I don't know what it's going to do next. So you're going to need to make sure you seed your calculator if you use calculator. Otherwise, the numbers are not going to be random. Everyone in class will have the exact same numbers if they're using the same type of calculator, TID4. Okay. Now, next thing I want to do is we're going to simulate tossing that coin 5 times in a row instead of doing this once at a time. So to do that, we do math, PRB, randint, and we tell it 0, 1, and then we tell it how many times we want it, 5 times. And there it is. So it went 0, 0, 0, 1, 1. It went, as you recall, that would represent, because you know it was easy to forget which one this was. That 0 was tails, 1 was heads. So we ended up getting 0 was tails, 1 was heads. We got 3 and then 2. Now, of course, if you try this, you can see whether or not you get all heads or all tails. And we actually tried in class. No one got all heads or all tails. It took many times of someone trying over and over to finally get all heads or all tails. Well, we don't have to limit ourselves to 5. We can do 100 coin tosses at a time. And we did this in class. Let me put calculator again. Now I arrow up to it twice to get the command. And now instead of saying 5, I'll change that to 100. Now I don't want to try and read 100 numbers off the screen, so I'm going to store them. So I press stow. I'm going to store them in a list. So second stat, so I get a list. I tell it stored in L1. It's generating them. It just stored 100 of them in L1 for me. Well, I can do this a bunch of times. But if I sum these up, if I sum up L1, it's going to tell me the number of heads I got since a 1 is head. So if I sum up all those values, it'll tell me how many I have. There's 2 ways I can do it. I can hit second list, go to math, and tell it sum up L1. So I'll show how that looks. So I can hit second list, math, come down to sum, and tell it sum up L1 for me. It told me I got 46 heads. The other thing I can do, and this is the way I like to do it, I do stat, calc, 1 variable statistic on L1. If we look, sum of my x's. It summed the list for me. It's 46. And I like this because I use this command all the time anyways. I don't have to learn another command or where something else is. I can just get it right here. So I have 46 heads. I can do it 100 coin tosses 5 times. And let's see how long that takes. So we pull up the calculator. We say we had to arrow up to get to the command. It looks like it's not going to let me. Nope, it's rerunning the stat. So you go math, PRB, randint, 0, 1, 100. Close our parentheses. Store L1. So I'm going to get different this time. Okay. Well, now I arrow up to get my command. Instead of saving it in L1, I'm going to go back and say, no, save it in L2. I have L2's loaded. I go up. This time I say, no, save it in L3. So each time I'm doing this, I'm simulating 100 coin tosses. I'm going to go up and try it in L4. We're going to see if I can make something happen that we haven't been able to make happen in class yet. Now we'll go up, we'll try it one more time. And this time we'll put inside of L5. Okay. Now what we want to know is how many times did we get those heads? And specifically, can we get over 65? Can we get heads more than 65 times? So I just got to check that sum, stat calc, 1 variable stat, L1. This time, 43 times. No, okay, we'll try it again. This time on L2. 54, that's okay. Well, it's 65 there. We're going to see if we can get 65. Change it to L3. And 51, no, not there yet. L4. 56. And we'll try L5. 57. So no, we didn't get it over 65 times. In fact, we had 40 people try this. Everyone tried 5 times. They did the simulation of 100 coin flips. No one got over 65. So we can make a pretty good decision now. If I had 40 people and nobody got 65 or more, each of us tried 100 times, 5 times, flipping it 100 times, then if someone did get 65, I'd be kind of suspect of that coin. If they got it 65 out of 100 coin tosses. I might even say it's 60, maybe even lesser, but I did get 57. So maybe 57, like, well, that could happen. That happened 1 out of 5 times. That could happen. But this, we had 40 people. That's 200 times. Nobody got 65. Odds are pretty good it's not going to happen just by chance. So, now, here's the thing though. Even if we did actually toss the coin 100 times, we wouldn't actually know for sure. We'd just be able to say a certain chance. Because remember, a coin could turn up 75 times out of 100. Or a bias coin, something that's weighted, could still turn up 50-50. That's how stats works. We're never going to know for sure exactly what we're talking about. We're never going to be able to say with 100% certainty certain things happened. But we will be able to rule certain things out to a certain degree. Okay, we'll have a certain chance or a certain probability that our choices are correct. That's what statistics works on, those chances, those probabilities. Okay? In order to do this, like I said, we did simulations. A simulation is just a sequence of random outcomes that model some situation. For example, so let's say I got a basketball player. They make 80% of their free throws. How can I use random numbers to simulate whether or not she makes a foul shot? You know, how many shots might she be able to make in a row before missing? Now, here's the thing. I could also have how long are we waiting before she misses? I'm just counting the number of successes. I'm counting how many times she makes it before she misses. Okay? But if I try to do this in the real life, some things will be thrown off. You know, as she's sitting there shooting these free throws, just so I can get a good idea of how many she makes before she misses on average, her arm's going to start getting tired. She's going to get sick of doing this. And eventually that 80% free throw success rate might go down just because I'm having her do this over and over. Okay? So instead we're going to use a simulation. And the first step is always the same. We have to see 7 steps. The first step is always the same. Identify the component. And a component is the most basic event we're simulating. So in here, we're talking about taking a single shot. That's our component. We want, how are you going to model the outcome? Now in this case, I'm going to use some random numbers that came in the back of the book. And on yours, it's actually page A77. I'm going to get a random digit. And it's 0 through 9. 0 through 7, that's 80% of them. That would be she makes a shot. 8 or 9, she missed. Explain how I simulate a trial. A trial is a sequence of events we're trying to investigate. And here, we're looking for how many shots until she misses. So I'm going to look at a series of digits until I hit an 8 or a 9. Next thing, you need to clearly state what is a response variable. Response variable, that's what we're interested in finding out. Well, it's counting the number of shots before she misses. Then, run several trials. The more trials, the better. We can probably narrow in on closer to what the actual number is if we have a large number of trials. And simulations are cheap. That's why we use them. So, here's my table of random digits got out the back of the book. For the sake of discussion, we're going to say that I just put a pencil on the page with my eyes closed, and that's where I'm going to start, that I start on row 1, column 1. So you see a series of digits, 9, 6, 2, 9, 9. Those are the first 5 numbers. I'm going to work across a row until I run out of digits, at which point I'm going to pick up my pencil, close my eyes, put it down somewhere on the page if I need some more numbers. But let's look at that first one, that trial number 1. Okay, so I'm looking just at those numbers. I made it zoomed a little bit easier to see. Well, if I start at 96299, well, she missed immediately. She got a 9 right away. She made 0 shots before she missed. Now I come down for my second trial. I just don't get to use that same number again, but I don't start all over. I just go to the very next digit. If I do that, 6 is she made a shot, 2 is she made a shot, 9, she missed. So she made 2 shots until she missed. The next one, I've used those numbers already, but again, 9 right away, she missed. She made 0 shots. Now I don't use any of those numbers. I'm moving over to the next set of 5. And the reason they're broken into these groups of 5 is just to make it easier to read the numbers. 0, she made the shot. 7, she made the shot. 1, she made the shot. 9, she missed it. So she made 3. Same thing. 6, she made the shot. 9, she missed. So she made 1. I've ran 5 trials. Now I could keep going until I've used this whole row. I could then use some more rows picking randomly. But these tables are really valuable. And by the way, you have to be used to using them. And if I give you a row and a column to go to, you won't be able to do that because that's how the tests are going to be designed. I'll give you the random numbers. You won't be allowed to just use your calculator to give you random numbers. How do I know you actually did it? Same thing in the AP exam. They'll give you random numbers. You have to use the ones they gave you. But now we're on step 6. Analyze our response variable. In this case, what was the average number of shots that they made? And if I average those up, I got, it's not going to come up, so we'll get to it, but it was 1.2. If I average 0, 2, 0, 3, 1, so that's 0 plus 2, 2, plus 0 is still 2, plus 3 is 5, plus 1 is 6. 6 divided by 5 is 1.2. So the mean number of shots she made before she missed was 1.2. I want to state our conclusion. There's my 1.2. I just came slightly out of order. Based on our simulation, we estimate the number of shots that she makes in a row is our statistic. That's kind of the Mad Lib kind of version. In this case, based on our simulation, we estimate she makes 1.2 shots in a row on average before missing. That's what we found. Now, let's say we change things up. How would our simulation change if her success rate was 72% instead of 80? Well, now a single digit would no longer be enough. It's a 72% chance. So I need to use a pair of digits, but I'm going to use from 0, 0 to 99. I'm going to use 0, 0 to 71 is a good shot, 72 to 99 a missed shot. And the reason I use 0, 0 to 71 instead of 0, 1 to 72 is if I do that, this is kind of the, there's a word for it, and I can't think of it at the moment. It's kind of standard how it's used. I'll start with 0, 0. The other thing is I don't want to have to use 100. I don't want to go 0, 1 to 72 makes it, and then from 73 to 100 misses, because that 100 requires 3 digits. And that would mean anytime I came with 132, I'd have to throw it away. So I can't use that. I don't want to use 3 digits. It would take me forever to do this. Now trial, this time they're going to run until I get a pair greater than 71. I say a pair because I'm using a pair of digits now instead of a single digit. So my trial changes a little bit. I keep going until they miss. Otherwise, it wouldn't change. My response variable is still the number of shots she made before she missed. Let's think about how might my trial change and my response variable change if I want to know how many shots she makes out of 5 at a crucial point in the game. So my trial, well, I look at 5 pairs of digits. Because she gets these 5 chances, so I'm going to need 5 pairs. Response, how many times did she make it in the 5 trials? I'll move that mouse out of the way. So it changes a little bit. I'm going to need 5 pairs of digits because she's going to get 5 shots. Response, how many times she make it in each group of 5? Now, what if I wanted the chance of her making both shots if she went to the line to shoot 2 after a foul? Well, look at 2 pairs of digits. Response variable, did she or did she not make both? Statistic, after many trials, what percent of the time did she make both? That would do it. That's why I want to know what's the chance of her making both. Then I need a percentage of her making both. And there are multiple ways you could have done this. Instead of 2 pairs of digits, you could say, I look at 1 pair of digits, then a second, If she made the first one, that's when I look at the second. Otherwise, I know she missed it. Why waste the other two digits checking just if she made the second but missed the first? If she missed the first, she didn't make them both. So there are multiple ways to do it. This might be the simplest way to do it. Just always look at two pairs. Okay. So let's want to change it. Now I want her to score in a 1-in-1 situation where she gets a second shot only if she made the first. Well, again, I look at a pair of two digits. If that pair represents the made shot, then I look at the next pair. If the first pair is a miss, she's done. She didn't get the second shot. Okay. And now I record as 0, 1. If both shots are made, record 2. That's how many she'd have made. Now, let's try another way. Mix this up a little bit. Let's say I want to randomly select 3 students from the class, speak at parent nights about how much they loved AP Stats. How likely is I get 3 boys? So a component would be what? It's the simplest thing I need to simulate. So in this case, how might I do that component? Well, I could number everyone in the class. And let's say there are 30 people in the class. I could use 0, 0 to 29. I could use a pair of digits from the random number table to represent the chosen student. That would be a component. So I'd move across the random number table 2 digits at a time in sets of 3, and that tells me who got picked. Now, of course, my random number table doesn't cut off at 29. So I ignore numbers greater than 29. And if I get a repeat, I ignore it because I can't draw a student and then pick that student again. Response variable. Now think about this. What do we want to find out? How likely is I'll get 3 boys? So response variable, it's yes or no. Did I pick all male? Statistic, find the percentage of trials that gave us an all male selection. I didn't have to do a lot of trials. If it happened 20% of the time, it happened 20% of the time. So I figured that out. So here's how this chapter wrapped up. Read chapter 11, knock out the homework, questions 1, 7, 9, 13, 22. But if you've watched the video to this point, I have something for you. I have a benefit for you. And here's that benefit. Let's see how much the video went. We're at 22 minutes so far in this video. So let's see what I can do to help you out. So that's our first couple questions. Statistics assume properly simulated length of checkout lines in a grocery store. The average length of the line will be 3.2 people. What's wrong with that conclusion? Well, I'm not going to give you the answers to your homework. But the question right after is kind of similar. After simulating spread disease, researcher wrote 20.4% of people contract the disease. What would the correct conclusion be? These are kind of similar. Just what went wrong. So my second one, really, the simulation suggests 24 might contract the disease, but the simulation doesn't tell us what actually happened, only what might happen. Where their statement, 24% of people contracted the disease, that's more of a statement. My simulation suggests 24% would contract the disease. Use that when you're thinking about the question you have. The average length of the line will be 3.2 people. Think about why that might be wrong. Right? You have a question about the election. Well, again, I can tell you the answer. But if you look, 2 pair, 3 of a kind, there's some similarities here. Now, mine's a little bit more difficult, 2 pair, 3 of a kind. I get drawing 5 cards random from a deck. What's more likely, 2 pair or 3 of a kind? A pair is 2 of the same denomination, in case you're not sure, picking a 2 and a 2, a 3 and a 3, a 4 and a 4, all the way up to a king and a king, or an ace and an ace. 3 of a kind, 3 of the same kind of card. I don't count 3 8s as a pair, that's 3 of a kind. I don't count 4 of the same kind as 2 pair, that's 4 of a kind, which, that's a good hand. So how could I simulate 5 card hands? And be careful, once I've picked the 8 of spades, I can't get it again. So how can I simulate a component? There's actually a lot of ways you can do it. So I've got one set of answers for this. Yours could be different if you had this kind of a question. First, a component is picking a single card. The outcome is the suit and denomination. Now, in this, because I need to make sure I don't get the 8 of spades twice. So to do it, I generate 2 random digits from 00 to 99. 01 through 52, I assign those to different cards in the deck. If I get 53 to 99, I ignore it. If I get 00, I ignore it. I would also ignore getting the same card twice in a single hand of 5. I'll probably get to that in a second here, though. Oh, there it is. Trials of 5-card hand. I keep pulling 2 digits at a time. Those 2 digits represent a card. But since I can't draw cards, I would have to ignore repeated cards. So if I get 52, I ignore 52. If I get it again, I'm sorry, 51. No, 52 is okay in this one. 52, I can't draw 52 twice. I can't get that card twice. Okay. Lastly, response variable. Response variable is whether simulated hand had 2 pair, 3 of a kind, or nothing. To find that, I divide the number of times it happened by the total number of trials. And something like this, since I'm using a computer, I'm going to be using a random number generator, I would probably do something like 200-300 trials and let the computer tell me if I made it. I'd have to program it, but I could also do it by hand if I had to. It would just take a little while, but it would still take a lot less time than actually dealing out 100 hands and evaluating each one of those hands and seeing what happened. So let's see. Multiple choice. Oh, that's your question. You take quiz with 6 multiple choice answers. Ah, my answers are already shown on the screen. Well, so I'm not going to answer yours. So my friend took it. They said they got all 6 right, but they claimed to have guessed blindly on every question. Every question had 4 possible answers, though. So let's see. If they had 4 possible answers, I use a multiple choice question. A component is answering a single question. I can pull random digits, 0 through 9. 0 is the correct answer. So it doesn't matter which one. I'll say 0 means they guessed right. 1, 2, 3, they got an incorrect answer. Now ignore digits 4 through 9. I don't need them. In fact, I can't even use them, not in a way that's really convenient. So each trial is going to consist of 6 usable random digits. In this case, repeats would be fine. I mean, they got the correct answer twice. They got it, and then the next one they got it. Response variable, did they get all 6 questions correct? Total number of successes divided by the total number of trials, that's the simulated probability of getting all 6 right. I'll tell you right now, there ain't going to happen too many times that someone guesses 6 questions correct. That would probably lead me to conclude there's something fishy with what they're telling me. The odds are really small that it could happen. So probably won't believe my friend. Blood donors. Again, I didn't make everything hide. Okay. Person with type O blood can receive blood from only other type O people. About 44% of the population is type O. At a blood drive, how many donors do you expect to examine in order to get 3 units? That's your question. This is mine. But there's some similarity. So think about this. How many in order to get 3? I'm going to have to assign a component, assign some numbers, and run a simulation. So my question, a couple want to have a boy and a girl. If they decide to continue to have children until they have 1 child of each sex, what would the average family size be? And assume boys and girls are equally likely, which they're close enough to equally likely. One way, I'm going to use random digits, 0 through 9. 0 through 4 is a boy, 5 through 9 is a girl. That's an equal chance of each. A trial, I just generate some random digits until they've got a child of each gender. Response variable, how many children until they had 1 of each. Simulated average family size is the number of digits generated in each trial divided by total number of trials. I decided to run 7. To do that, I did randint 0 through 9 50 times, loaded that in L1. I started reading down L1. I get 9, 9, okay, that's 2 girls, 1, that's a boy. My first trial, and I'll mark it just so we can see a little bit better. That's my first trial. 3 children in order to get 1 of each. 5, that's a girl. 4, that's a boy. My second trial was 2 children. 7 and 0, again, 2 children. Third trial, 3, 9, again, 2 children. Next trial, 2, 7, 2 children. Sixth trial, 9, 2. Oh, I made a boo-boo. I made a boo-boo when I ran this. Should have just been 2 children, 9, 2. Now my last trial, 3, 0, 9. So I made a boo-boo when I did my math here. So it's 3, 2, 2, 2, 2, 2, 3. So 3, 2, 2, 2, 2, 2, 3. And that will give me 7 trials. So I have 1 too many 3s over here. So my final solution is going to be off by a little bit here. Okay. I was saying, based on this simulation, I estimate that such a family on average has 2.4 children. But my math had a mistake. In trial number 3, in trial 6, I thought I had to have 3 people in the family to make it happen. So I made a typo in it. It's actually a little bit less than 2.4. But if I think about it, I do expect the answer to be more than 2. Because even though boys and girls are equally likely, they're going to keep going until they have one of each. Well, they can't have less than 2 and have one of each. So sometimes it'll happen around the second child, but sometimes it's going to make more. Sometimes it might take 3, could even take 4. It's even possible it could take 5 or 6. So the average, it would make sense it's going to be a little bit more than 2. And that's it. So I want to give you a little help with some of the questions you have on the homework, but go ahead and try that out. This came in right at 30 minutes, the whole chapter, and something to maybe help you out on your homework questions. But I look forward to seeing you all in class.